Asymptotics is where econometrics starts to ask a different question. Instead of asking what is exactly true in a finite sample under strong assumptions, we ask what becomes approximately true as the sample size grows. That shift matters a lot because many exact assumptions we used earlier, especially normality, are not very realistic in applied work. The first key idea is consistency. An estimator is consistent if it gets closer and closer to the true parameter as the sample size grows. For OLS, the familiar exogeneity assumptions are enough to deliver that result. So if we have a bigger and bigger sample from the same population, the sampling distribution of the OLS estimator tightens around the truth. That sounds similar to unbiasedness, but it is not the same thing. Unbiasedness is a finite sample statement about the estimator being centered at the truth. Consistency is a large sample statement about where the estimator converges. You can have one without emphasizing the other. In practice, consistency is often the more important long-run concept because it tells us whether more data are actually moving us in the right direction. The probability limit formula makes this intuitive. In the simple case, the probability limit of beta hat 1 equals beta 1 plus the covariance between x and u divided by the variance of x. If x and u are uncorrelated, that extra term vanishes and OLS is consistent. If x and u are correlated, the estimator converges to the wrong number. So asymptotics does not rescue bad identification. It only tells us where the bad estimator is heading. That is why omitted variable bias still matters in a large sample world. If the omitted variable is correlated with the included regressor, the coefficient does not slowly drift toward the truth as n grows. It slowly drifts toward a biased probability limit instead. The same sign logic we used for bias earlier still applies. Asymptotics just gives us a cleaner language for describing the long-run consequence. Now think about normality. Many real outcomes are not even close to normally distributed. Counts cannot go below 0. Participation rates are bounded. Arrest counts pile up at 0. So if we insisted on exact finite sample normality before doing inference, applied econometrics would become almost unusable. That is the problem asymptotics solves. Under large sample conditions, the standardized OLS estimator becomes approximately normal even when the underlying errors are not exactly normal. That means the t-statistics and confidence intervals we know from the classical model still work approximately. The word approximately is doing the work here. The inference is no longer exact, but in many settings it is close enough to be very useful. How large does the sample need to be? There is no universal answer. It depends on how far the real data are from the ideal assumptions. But with several hundred observations, the large sample approximation is often good enough in cross-sectional work. That is why applied researchers frequently report p-values and confidence intervals without making a big issue out of exact normality. So the practical lesson is this. Asymptotics gives us two major benefits. First, it tells us when estimators like OLS converge to the truth. Second, it lets us keep doing inference even when exact normality is unrealistic. But asymptotics is not magic. It does not fix endogeneity, omitted variables, or bad instruments. If identification is broken, more data just make you more certain about the wrong answer. Asymptotics is one of the big bridges from textbook econometrics to real empirical work, because it lets us keep useful inference even when the clean exact assumptions fail. Next, we turn to instrumental variables, which is what we need when endogeneity itself becomes the central problem.